Hi, and welcome to 10.3 Conservation of Charge. Let's start by doing three review type questions from like 10.2, and then 4, 5, and 6 have to do with the law of conservation of charge. So with number 1, it says a positively charged rod, shown here, is held near the knob of a neutral electroscope. So this electroscope here is neutral. There's going to be the same number of positive charges and negative charges, meaning like the same number of positive protons and negative electrons. So it says draw plus or minus signs in the knob and leaves sections of the diagram to the right to represent the charge distribution of the electroscope. Since it's neutral, we want to make sure we draw the same number of positive and negative signs. And we just have to think about where the negative electrons would be going and where the positive protons wind up. I mean, the protons don't really move around, right? So let's draw some neutral atoms. Okay, so a neutral atom has the same number of protons as electrons, so I just drew a simplified version of an atom. I have one proton and one electron here. So I have 1, 2, 3, 4 neutral atoms shown in the knob, and 1, 2, 3, 4 neutral atoms shown in the leaves. And the thing about an electroscope is it's all made of metal, or these would be like gold leafs if you're talking about a gold leaf electroscope. Then that means that it's a conductor, so the electrons are free to move around within the object. So let's think about it. If you bring a positively charged rod close to this electroscope, the electrons are going to be attracted to this positive rod. So, and since it's a conductor, the electrons from the bottom of the leaves are going to go up here, and now all of a sudden they're all kind of congregating up in the knob. And even though the leaves were initially neutral, it had the same number of protons and electrons. Now, as you can see, it's positively charged, and that's why the leaves separate. So there's this force of repulsion. Since they're both positive over here, they're going to repel each other away because positive repels positive, like charges repel. And as you can see here, we have plenty of negative electrons on top, so the knob becomes negative. So that's the general concept. If we were just going to represent that by doing positive and negative signs, you could just say, okay, this is going to be positive because the electrons left the leaves and they went up here. And I'm making sure I draw the same number of positive charges as I do negative charges because, again, it's a neutral electroscope. And we're not giving this thing a charge. What we're doing is we're polarizing it. And we're like inducing a charge, but we're not giving it permanently charged. As soon as you move this rod away, the leaves will come back together because it'll be neutral. And that's the idea with that one. Number 2 says when a neutral metal sphere is charged by contact with a negatively charged glass rod, the sphere gains or loses electrons. Okay, so if it's charged by contact, so it's going to be both the same charge. As we talked about in 10.2, if you're looking for an explanation of what's the difference between charging by contact and the next one says charging by induction, I explained the difference in the beginning of the 10.2 video, so go watch that. So it's going to become negative. So the glass rod, the sphere becomes negative. Let me draw that over here. And if the sphere is negative, that means it gained electrons, right? Because electrons themselves are negative. So now we have an excess of electrons, so it gained electrons. Number 3, when a neutral metal sphere is charged by induction with a negatively charged rod, the sphere, okay, so this is going to be opposite charges. How do I know that? Again, because we're talking about induction. And it's going to become positive, so the sphere becomes positive because this thing was negative. And if something becomes positive, like we talked about with the leaves, the only way to become positive is if you lose electrons. So we're going to lose electrons there. Okay, so that's kind of a review. Number 4 has to do with the law of conservation of charge. So let's take a look here. It says a metal ball with an excess of 11 electrons is touched to an identical ball with an excess of 15 electrons. So let me draw the situation here. So we have our first sphere, and I drew like 4 neutral atoms here just to represent the fact that, yeah, there are protons here. It's just they're being balanced out by some electrons, but we have an excess of electrons. So this one has 11 excess electrons, and they're all kind of evenly distributed on the surface of the sphere because they're repelling against each other. So they want to be as evenly distributed as possible, so they're as far away from each other as possible, because again, they're repelling away from each other. They all have a negative charge. So now I'll draw the other sphere that has 15 electrons on it. Okay, so as you can see, this is even more negatively charged. There's more excess electrons on this. And it says that they touch each other, right? So it's touched to an identical ball, and it's metal, so that means it's a conductor. So as soon as you bring this into contact with the other one, like that, now since it's a metal, they're both metal, the electrons are free to move from one object to another. And since they're all repelling against each other, they're going to, again, try to become evenly distributed, but now they have both spheres to spread out. So what you have to do is you figure out what the total number of electrons is. So you do 11 plus 15. That's a total of 26 electrons. So for the total amount, there's 26 electrons for both. And now we want to evenly distribute them. So there's 2 spheres, divide that by 2, and now there's going to be 13 electrons on each sphere. So the one that has 15, we need to subtract 2 of them. So one of them goes over here, and then another one goes over there. And now we have 13 electrons on each sphere. And then you could even separate them out. And you have 13 electrons here and 13 electrons on the other side. So this shows the law of conservation of charge, because it's basically saying before they touch, you have some kind of total charge. And then after they touch, the total charge remains the same. So before they touch, when you add up the charge for each sphere, you get 26 electrons. And then after they touch and they become evenly distributed, and you could separate them out again, you get the same answer. There's still 26 electrons there. Okay, so that's kind of the law of conservation of charge, is that you can't just gain electrons from out of nowhere or lose electrons into thin air. They have to go somewhere. So in this case, they were transferred from this sphere to this one. So you could transfer the electrons, you just can't gain them out of nowhere from outside of the system, whatever it is. So let's talk about the questions. For A, it says, what is the number of excess electrons on the second ball after the balls touch? Well, it's going to be the same for both. So for A, it's 13 electrons. 13 excess electrons, right? And then B says, what is the charge on the ball? Oh, is the charge on the ball positive or negative? Since they are excess electrons, it's going to be negative. And it says, what is the charge on the first sphere after they touch? So it's not asking what is the number of electrons, excess electrons on the first sphere. It's asking for the charge. So what is Q? And then, so now we know Q. We can figure it out because we have that formula. Q is equal to NE. The total charge is equal to the number of electrons times the charge for each electron, which you can see in your reference table, 1.6 times 10 to the negative 19 coulombs of charge. So this is the charge, the elementary charge. It's the charge for just one electron. But we don't have just one excess electron. We have 13 excess electrons. So you do the multiplication and you get a total charge of negative 2.08 times 10 to the negative 18 coulombs. And if you're wondering where I got E from, you have to look in your reference table. It's right here on the front. This unit is pretty heavy on this particular table. You have to know what all these constants are. So here's one. The elementary charge, it's the charge for one proton if you choose to make that positive. And if you're talking about an electron, you just choose to make that negative. So in this case, it was negative 1.6 times 10 to the negative 19 coulombs. That's the charge for one electron. All right, let's go see the next problem. So it says, number 5 says metal sphere A with a charge of positive 7 coulombs and an identical metal sphere B with a charge of negative 10 coulombs are brought into contact and then separated. So it says, what is the charge of sphere A after they're separated? So you have your two spheres, and sphere A has a charge of positive 7 coulombs. Sphere B has a charge of negative 10 coulombs. So you kind of have to visualize, if you wanted to really understand this, you have to visualize where the electrons are going, right? So since this is a positive charge, that means that not all of the atoms are balanced out by electrons. So here maybe we have only one. All right, if we draw it like this, it's easy to see that, yeah, there's one neutral atom here, but these atoms are begging for an electron. They want to be balanced out. They want to attain some kind of equilibrium, but they can't because they don't have enough electrons. They're deficient some electrons. Whereas with sphere B, you have not only enough electrons to make this neutral, like this, you actually have an excess number of electrons. So let's draw maybe 4 electrons here. So when they come into contact with each other, what happens is we'll move this over. They come into contact. Now the electrons are free to move. They want to attain some kind of equilibrium. Basically, these guys are all repelling against each other, looking for more room. And not only are they trying to get away from each other, these guys are attracting the electrons away. So some of the electrons will shift over to try to attain an equilibrium. So we'll move, maybe this guy comes over here, and maybe this guy comes over here. Actually, enough electrons move. I didn't draw enough. Enough electrons are going to move over here and to make both things negative. How do I know that both things are going to be negative? Let's see. If we do the calculation here, oh, and then you separate them out, right? So the number of coulombs are going to change. And it's going to become negative. And then you separate out the spheres again. So we're basically charging the sphere by contact, leaving them both with the same charge. So if you think back to 10.2. All right, but let's reset this a little bit. We're looking for the total charge. So you have the charge of A plus the charge of B. The total charge can't change. That's the law of conservation of charge. So this is positive 7 plus negative 10. And these are coulombs, right? So the total charge is equal to negative 3 coulombs. So when you put them together, they share the charge. Like the electrons go from B into A and balance out. And when they're together, the total charge has to stay the same. So you have a total charge of negative 3 coulombs when they're together, and then they separate out again, and now the charge is evenly distributed, so the electrons have to transfer over. So now an equilibrium has been reached, and we separate out the spheres again, and we divide this negative 3 coulombs evenly between the two of them. So you have to do negative 3 coulombs divided by the two spheres is negative 1.5 coulombs on each sphere. You want to make it so that there's an equal number of coulombs, the equal number of charge on each sphere, but when you add the two charges together, you still get the same total charge because charge has to be conserved. All right, the total amount of charge has to remain the same. And that's the idea for this. That's all you have to do. You just add the two charges together and then divide by 2. Or if you have 3 spheres and they all are equally in contact with each other, you divide by 3. All right, that's the idea. So it says, what is the charge on sphere A after they are separated? It's going to be negative 1.5 coulombs. And it says, what is the number of excess protons or electrons? Well, we know it's going to be excess electrons because sphere B is negative, and so is sphere A. And it's represented by that excess electron there. But it says, what is the number of excess electrons on sphere B after they're separated. So let me move this work over here. That's the idea there. And then let's calculate this charge. So again, for B, I'm going to do Q is equal to NE. Now we know the total charge for B is negative 1.5 coulombs. We're looking for the number of electrons, and each electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. So you do the division, and you get the total number of electrons, about 9.4 times 10 to the 18 electrons. So it says which sphere gained electrons. If you'll remember, sphere A started out as positive. It was deficient in electrons. And sphere B had plenty of electrons to give away. And you could tell because this is positive and this is negative, sphere B has a lot of electrons to give away. So the electrons were actually transferred from sphere B to sphere A. So which sphere gained electrons? A gained electrons, and sphere B lost electrons. All right, let's do number 6. Okay, so metal sphere A with a charge of 4 coulombs and identical metal sphere B with a charge of 9 coulombs are brought into contact and then separated. So in this case, you have the two spheres again. So you have A and B, and I drew 10 protons on each one. So since A has a charge of positive 4 coulombs, I'm going to draw an amount of electrons so that there are 4 protons left over. So I want to draw like this, spread it out. So I drew one too many here, just like that. So we have 1, 2, 3, 4 excess protons. So I'll use that to represent the fact that this is positive 4 coulombs of charge. Now, positive 4 coulombs isn't equal to 4 electrons, right? As we could see from the Q equals NE formula over here. It actually takes a lot of excess protons to make 4 whole coulombs of charge. But I'll just represent this as the numbers work out, so I could use I could draw that to represent that many protons. I'll do the same thing for the second one, where this is positive 9 coulombs of charge. But since I drew 10 protons and I need positive 9 coulombs, let's use just 1 electron. Now we have enough to represent the fact that, okay, there are 9 positive charges shown here, and there's 4 positive charges shown here, and we could say each one of those red circles represents 1 coulomb of charge. So now, when they're brought into contact, what do you think is going to happen? It says, what is the charge on sphere A after they're separated? So let's bring these into contact. And now they're sharing this total charge. So again, you could like write this formula. The total charge is equal to the charge of A plus the charge of B. So the total charge is equal to 4 plus 9 coulombs. In this case, they're both positive. So the total charge is equal to positive 13 coulombs. So now we want to not write positive 4. That goes away. Not duplicate, but delete. This goes away. This goes away. And you're left with a total charge of 13 coulombs. And the electrons want to go to where there's more protons. They're attracted to the positive sphere B, the more positive sphere B. So I'm going to try to figure out how many I should move over. Let's see, if we split the positive 13 coulombs between the two spheres, you get 6.5 coulombs on each sphere. So we want to move enough electrons. It's not really going to work because I'm going to have to split up an electron in my diagram here. And we all know you can't split up an electron, right? But remember, each electron represents a whole coulomb of charge. So we want to try to at least try to move over as many as we can without having to split up the thing. I'm just trying to show that where the electrons are moving, right? So that's the whole point. So we can't show it in this case because we want to not split up an electron, but hopefully you saw that the electrons moved from one object to the other. They went from sphere A to sphere B, which is going to be one of the next problems here. So the total charge on each sphere after the separation is 6.5 coulombs of charge. So we move this over. And now we should have positive 6.5 coulombs on each sphere. That total charge gets divided between each one. So it says, what is the charge on sphere A? Positive 6.5 coulombs. What is the number of excess protons or electrons on sphere B after they're separated? So sphere B is still positive. It didn't gain enough electrons to make it negative. So it has excess protons. So let's move this over again. And let's do the Q equals ME. The total charge is equal to the number of excess protons times the charge for each proton. So now we could do the total charge. We know is positive 6.5 coulombs for sphere B. And then that's equal to the number of protons times the charge for each proton is the elementary charge, 1.6 times 10 to the negative 19 coulombs. And the coulombs cancel out to give you just a number. So this is 4.1 times 10 to the 19 excess protons on sphere B. All right, so that would be like what we represent by this. But obviously, I'm not going to draw in 4.1 times 10 to the 19 protons. But that's why, the math didn't really work out. In order to draw the 6.5 coulombs of charge, I would have had to split up an electron in my diagram, which represents 1 coulomb. But I didn't want to do that because it's important. You never want to split up an electron. So it says which sphere gained electrons, and hopefully you saw by the diagram I drew, we saw that the electrons travel into sphere B. So sphere B gains the electrons. And how can you tell that without having to draw a crazy diagram? What if the numbers are kind of weird? Well, you want to look. Okay, this is positive 4 coulombs, and this is positive 9 coulombs. This is very deficient in electrons. It needs electrons badly as compared to this one. I mean, yeah, this one needs electrons in order to be neutral, but sphere B really needs the electrons. So this one has enough electrons to give this guy, and they wound up being positive 6.5 coulombs each. All right, so this one became more positive. It went from 4 coulombs to 6.5. It became more positive because it lost electrons. And the 9 coulomb one became less positive. It was 9 coulombs. Now it's only 6.5 coulombs of charge. It became less positive because it gained electrons. So that's another way to think about it. But I wanted to draw the picture so that it kind of helps, I think, visualize, especially when you have 2 positive charges. It's kind of hard to visualize where the electrons are going. Just think of the positive 9 being more positive. It needs more electrons than the positive 4 did, so it'll go there. All right, that's about it. Have a good day.